We still in the other room on the top then?
Yes, we are. We're in two different rooms. We're lucky to have a room at all today. Scour high and low to find us a day room. Okay, so let's pick up from last time where we were. Any questions on what we did last time or any other issues? Yeah, I was hoping to do that. Way to okay, so let's pick up where we were then. We were talking about how to generate random numbers according to some distribution. Okay, and last time we looked at inverse transform statement. Okay, remember how we did the exponential and we started with a linear distribution of random numbers, but we were able to transform it into random numbers that were drawn from an exponential distribution. Cool, you all remember that? Okay, so there's an issue with this, we talked about it briefly last time, is that in this process, we first have to find the cumulative distribution function. We have to be able to integrate the function. And then we have to be able to invert the function. This is not always the case. And in fact, for the distribution we most often want to use, this is not the case. Okay? Distribution we most often want to use, Gaussian, the normal distribution. Okay? So let's look at Gaussian. If we try to do the cumulative distribution function of a Gaussian, it's going to look like we have to make sure that our functions are properly normalized. Okay, and sigma here is the standard deviation, so we have 1 over the square root of 2 pi sigma squared. Then what we're going to do is integrate that from the left-hand limit, which is going to be negative infinity, up to some right-hand point. And remember, this is the slider that we use to figure out where we are in the ratio of the areas. And so what we're going to do is we're going to be integrating e to the negative x squared over 2 sigma squared. And let's put a little prime on this x. This is just a dummy variable for integration to distinguish it from our upper limit. This is not a particularly nice looking integral, and in fact, there's no easy closed form solution to this integral. Okay, this is, however, it's a very common integral. This is defined to be the error function, x over the square root of 2 times. And just to write down the error function of x is equal to, it's defined to be this, 2 over pi, the integral from 0 to x, so x is the upper limit, e negative t squared dt. Okay, so if this is what we have, obviously this is going to be very easy to invert, okay? And we can't do it. Okay, so the inverse transform sampling method doesn't work for a normal distribution. Okay, which is a bummer because that's what we want to use a lot. Okay, so there are other ways of generating these random numbers according to some distribution. Okay, we're going to talk about a couple of them. But first, this is one that I'm not going to derive, but it's one that's going to be useful for the course. Okay, so an important one is called the Box-Muller transformation. Okay, and what happens in this technique is that you select a random number between 0 and 1. In fact, you select two of them. Okay, R1 and R2, which are evenly spaced on the interval from 0 to 1. Cool. So we just draw two random numbers from our usual random number. And then what we do is we can generate another pair of random numbers. So let's call these, let's put a G in front of it just to indicate these will be according to a Gaussian distribution. Okay, and the first one is sigma negative 2 ln R1 multiplied by cos 2 pi R2. And the other random number we can generate from this pair, as you might expect, I don't have it here. Yes, okay, ln R1 sine 2 pi R2. Okay, and remember we assume that the two random numbers that we pick initially, R1 and R2, are independent of each other. We put them through the Box-Muller transformation. We get another two random numbers that are, again, independent of each other. But now, if you were to run them all through this distribution, through these functions and plot the distribution, we would get a Gaussian instead of a linear distribution. Okay. Cool. We're just going to leave that sigma there. So that would be, so the normal, that's a standard deviation of the normal distribution. So you can tune the width of it. Okay. So it's the same sigma we have over here. Okay. Cool. But don't want to actually derive this. Okay. We're going to look at a couple of different ways of generating random number distributions, including a Gaussian. Okay. All right. Any questions on this? So this is kind of a black box, at least for now. Okay. I just want to present this result because we're going to use it in the simulations. Okay. Can anyone think of another way we could generate a random number distribution that yields a Gaussian?
Average a bunch of random numbers.
Yeah, why does that work? Yeah, okay, we can use the central limit theorem. Okay, so what the central limit theorem tells us that we can take any distribution at all. We can randomly sample from it a bunch of times. Okay, so let's say we sample from it n sample times. Then we take the average of those samples that we just drew. Okay, and now we do a distribution of those averages. And what you'll get every time is a normal distribution. Okay, it's one of the reasons it's called the normal distribution. Everything tends to this. Okay. Yeah.
What do you mean by distribution?
Okay, so let's say we have a distribution of random numbers, right? That is linear between 0 and 1. Okay, so it has all equally probable to be between 0 and 1. Okay, and so you draw a bunch of random numbers. So you're going to pick one from over here, one from over here, one from here, one from here, right? These are just numbers you're going to select out. Okay, so this could be 0.1, 0.8, blah blah blah, right? And then you average those. So let's say you do that 10 times, and you calculate the average of those numbers. Okay, now you make a new list, which is just all those averages. Okay, so you do that a whole bunch of times, n times, and now you plot that distribution. You're going to end up with a normal distribution. Okay, and to give a kind of qualitative picture into that, you can kind of think about why that might happen, okay? Because in this distribution, we're equally likely to draw a random number from anyone, right? But if we draw 10 random numbers, what are the chances that they're all over here? Not too likely, right? So when we take the average, it's going to tend towards it. Okay, same as if you take 10 numbers that they're all over here. Okay, it's not very probable. So by averaging, you're going to tend towards the middle. Look confused. Okay. Does that make sense? Yeah? Okay, so this obviously does not derive the shape, but we would expect something that, if we plot it, would increase, have a maximum around the center, and then decrease on the other side. Okay, turns out to be a Gaussian shape. Okay, again, there's ways of deriving this from the binomial theorem. Okay, but in this course, I'm more interested in actually programming this stuff. So what we're going to actually be doing is looking at a program how we can verify this. Cool. Okay. So one thing to note: we don't actually want a random number that goes between 0 and 1, because for our purposes, what we want to try to do is generate a Gaussian distribution that has a mean of 0. Okay, so it has a mean of 0, and we want it to have a standard deviation of 1. Okay, so I don't want random numbers that go between 0 and 1. What I want to do is shift the distribution so that my random numbers go between -0.5 and 0.5. Okay, because this way, this is centered on 0 all the way. Cool? Yeah?
It doesn't matter if it's centered on 0.
Yeah, that's right. Yeah. You just have to make sure, yeah, you just have to make sure that the, yeah, it could be 2 points. Yeah. But you have to be careful, okay? And we'll talk about why you have to be careful in a second. Okay? But the first thing we want to do is just shift it so it's centered on 0. We want a mean of 0. Okay, so how can we do that? Well, we already know how to generate a random number, right? So this is the code we were using. We're casting it to a float because single precision was good enough here. We take rand, we divide it by a rand max. So now what we're going to do is just minus off 0.5 on that. And obviously we go from a domain of 0 to 1 to -0.5. Cool? Okay. The other criteria is that we want a standard deviation of 1. Okay. So let's calculate what the standard deviation of this distribution is. Okay, so anybody know how we can calculate the variance of this distribution? This is a distribution where rho of x equals 1 over the interval -0.5 or, yeah, -0.5 to 0.5.
So from scratch or like taking the result from 0 to 1?
So what, like, what's the formalism for calculating the variance of a distribution? What do I write down here?
Average value of the square deviation from the mean.
Right. So what I do is I can calculate the second moment of the distribution, right? By going x squared rho of x dx. And then I average off the average squared. Okay? What is the average squared here? 0. Okay? That's the first thing we get. Forget about this term, we're just looking at this. What is my rho of x? Yeah, what's that equal to? 1. 1, right? We have equal probability of it and selecting anywhere on this interval, so it's just 1. Okay, so we just have the integral of x squared from 0 to 1. What are we going to get? We need a third. Sorry, it's not 0 to 1. It's -0.5 to 0.5. sorry, my apologies. Because remember, we shifted the domain. Cool. So this goes from negative 0.5 to 0.5. Wrong in my notes. Okay, and what we end up with is this is equal to 1 over 12. Cool? Okay, so this is the variance of our input distribution. Okay, so in order to get a Gaussian out the other side, we need that has a standard deviation of 1. So then if this is the variance, this means the standard deviation of this distribution is 1 over the square root of 12. So what we really need to do is modify so we have the same definition we had before. Sorry. I'll put it out in front. We need to include this root 12. We need to scale the random numbers that we draw by root 12. Okay? And this means we will get the appropriate standard deviation of our final function. So we just put root 12 times then this stuff here. So the float, rand max, and then we want to minus, this whole thing has to be minus. Okay, yep. Okay, so we want to end up with a standard deviation of 1. Okay, but the standard, it's not a very good drawing. This needs to go edge to edge. The dartboard itself has a radius of 0.5. So it's exactly inscribed within my square. Okay? So I want to calculate pi. I don't have any tools to do this, but I do have a random number generator. Okay? How can I do this? Suggestions of how to proceed. What can I do? Sorry, what was it? So this is my system. Cool. And I want to be able to calculate using this system and just a linear random number generator. I want to calculate the value of pi. What is pi equal to? Numerical. We don't have Google to just say pi. Yeah, we know the answer. How do we get there? Any ideas? Based on what we were just discussing about rejections.
So we'll start with the formula for the area.
Oh, what do you mean? Give me a qualitative picture of what we're going to do.
We'll calculate the area numerically, and then we'll relate that to pi.
Okay, calculate it numerically. How are we going to do that? How are we going to do that? Monte Carlo.
Same thing we did in there, basically.
Yeah. What do you mean? Yes. Okay. So we keep taking random numbers between 0 and 1 in both x and y. Okay. And these give us different points. If our point, okay, if r for the point is less than or equal to, so where r is the square root of x squared plus y squared, if that is less than or equal to 1, we accept.
0.5.
Yes, thank you.
R is going to be x minus 0.5 squared.
Yeah, you're right.
I think you're right.
Now I need more room. Plus y minus 0.5 squared. That is less than or equal to 0.5. I made that same mistake when I programmed this for the first time. I was coming up with horrible estimates of y. Then we accept, okay? So we'll have these two numbers. Else reject. Okay? And so we just lose track of the number of times we accept it and the number of times that we reject it. All right? And so the ratio of the acceptance over the acceptance plus rejection what's that going to be equal to? What's the ratio in areas? Nope, not pi. What's the area of a circle? Yeah, pi r squared over length times width. Both of these are 1. Okay, so this is 0.5, so this is equal to pi times 0.5 squared. Cool? So we can use a random number generator to calculate pi.
This is good for calculating something that you can compare to some solutions that you already know at the time, predetermined. So if I had a distribution, I don't know if this case would actually happen, but
Okay.
if it were like a swappy distribution,
Yeah.
and I don't know what it is that even something I'm thinking about?
So that's harder, and we're not going to talk about that here. So what we're assuming here is that we want the random number according to some distribution that we know. Okay, it doesn't even have to be analytic. We can just know to some precision numerically what the probability at each one of these is. Okay, but for a distribution we don't know, then whole other. Cool.
Yeah.
We're assuming we know the distribution. Okay, so the goal of this exercise, though, is to just show you that you can use a random number generator to calculate a lot of things. Okay, and here we're using it to calculate pi. And in fact, you can broaden this. You can use a random number generator to calculate the area under any curve. What do we call the area underneath any curve? It's the integral. Okay, so you can use random number generators to solve integrals. Cool. And as you probably know at this point in your academic career, okay? Yep.
On the left-hand side, you have accept over accept plus reject.
Yeah.
When you say accept, those are the number of points that
Yeah.
you pick, or the
Yeah.
values.
So every time the point ends in here,
Right.
we have this counter that we just introduced.
So you
That's
just,
what the plus plus means.
so
So I'm using C notation here. So if any of the syntax is Dan's line. If any of the syntax is confusing, let me know. Okay. The reason I'm doing that is because that's what we're going to see in the program right now. So it's easier to compare back. Cool. Yeah. So anything that falls in here is accepted. Anything that falls in these areas is rejected. Okay, but the ratio of the areas then is these points divided by all of these. So this is just the number that we drew, the sales that we drew. Cool. All right.
okay.
Coming up. Here we go. So here's the program. Again, it's a very simple program. All we're going to do is we have a main loop here that we're drawing our X and Y samples. We're calculating the radius. And we're seeing if it is less than 0.5, we accept it. Isn't, we reject it. then I can do this for different numbers of iterations, okay? So this calculates just a single point. Now here I have my n set to be 10 to the power of whatever this is. So again, I can go from 0, 10, 100, all the way up to like a billion, okay? And so what does it look like? Here's if I plot the value that I get for pi. Oh, sorry, at the end, we, yeah, you can't see the output here. These vectors of the hundreds. So here I'm just normalizing by the 0.5 squared to make sure I'm actually outputting pi. Cool? So I plot that, and this doesn't fit on the screen. But plot that result I get, we're doing it an increasing number of times. Obviously, we get big errors when we have low sample sizes, but then this quickly starts to converge. Cool? Yeah? Okay, so you can use rejection sampling to generate random numbers according to any distribution, no matter how wacky. Okay? The efficiency of it will depend on the distribution itself. Okay? But in principle, and furthermore, the point I'm trying to make is you can use a random number generator to integrate functions. It's pretty cool. All right? Okay. That is it for random number generation. Let's talk about doing some more simulations here. Okay. Let's get back to simulations. Okay, so remember, we have our whole idea behind molecular dynamics is F equals ma. And so with this, we can model the motion of particles when they're experiencing forces. Before we get too heavily into that, let's take the simplest possible multi-particle system we can think of. Any ideas what this might be? Ideal gas. Okay, let's put a bunch of particles into a box, and we want it to be as simple as possible. So they're obviously going to interact with the walls of the box, but they will not interact with each other. Okay, this is the ideal gas. All right. Lost the marker. Okay, so in order to do an ideal gas simulation, we need to start with, we're going to have a bunch of particles, n particles, and we need to assign each one of them a velocity. Okay? Velocity of a sample of particles. Physics, anyone remember what this goes by? Yeah, the Maxwell-Boltzmann distribution of velocity, right? So our rho here, we're going to have a standard deviation of kT over m. K is a Boltzmann constant, T is the temperature, M is the mass of the particle. Okay? So this is just a thermal energy over the mass. Cool? And then the distribution of velocities is M over 2 pi kt, e to the negative mv squared over 2p. Yeah, this is a result that we can come back to later when we talk about the equipartition theorem more generally. Okay, but for now, let's just take this as a given. Okay, so we're going to start with n particles in a box. We want them to have an appropriate distribution of velocities. So we're just going to select the velocities from distribution here. Fortunately, with everything we just talked about, we know, about 4 ways to make sure we get velocities according to this distribution. Cool? Okay. So the velocity, if we calculate the average velocity, what's that going to be equal to? This distribution? average velocity.
It's vector should be 0,
0, right?
Okay.
because our box should be moving.
How about the average square velocity,
That's better.
right? Which is obviously related to the kinetic energy.
8 kT over 5.
It's a half kT. Okay, we're just doing this in one dimension. Okay, just to drive this in one dimension. Okay. This needs a mass in it though. Oh no, sorry. What I want to do is define this in a 2D system. Okay. 1D is too boring, and 3D is too hard to visualize, so we're going to do it in 2D for now. Okay. And so if you take the average of this in 2D, you get the half. Cool? Good?
That's like the RMS velocity.
Yeah. Yeah. Root mean squared. Any questions? Yeah, right back there? Yeah? Kind of? Yeah? Okay, so all we're doing is we're assigning a bunch of velocities to this part. Okay? Sorry, let me back up. What's our system going to look like? We're going to take a box like this, and we're going to put n particles in it. Well, to start our simulations, we need some initial conditions. We need initial positions for the particles, and we need initial velocities for these particles. When we're building our box, the initial positions are pretty easy since these don't interact. We can just take a random number between here and here, and between here and here, and plump down the particles. Okay, we're done for initial position. We don't even have to worry about if they overlap. Initial velocity, we have to be a little bit more careful. Okay, we don't, if you take the sampling of velocities of a bunch of particles, it's not some linear distribution, okay? And it's not that they all have one velocity, okay? The result, as you would expect for anything, it's a normal distribution, okay, in the velocity. So all this means is that when we set up our system, we can assign the velocities from this galaxy. Cool? That's it, all right? So we can define the system like this. And what we just figured out is that there's a velocity which is related to the thermal energy kT. Okay? So if we change the kT of our system, we change the velocity of our particles. Okay? So this is an important variable. Cool? What else do we have? Well, we have n, we have our number of particles. What else do we have? Well, we have the area, which in 2D is our area, and 3D, this would be our volume. Okay? Let's just write down D. In this case, it's A for area, and 3D would be whatever. Okay? Now, the particles don't interact with each other, but they do interact with the walls. What happens when a particle hits a wall? Well, totally conservative forces here, okay? Elastic collisions. Particle goes this way, hits a wall with some velocity v. It's going to bounce right back. Cool. All right. So all these particles inside the box bouncing outward are going to give us a pressure. Okay. So let's call that P. All right. We know the relationship between these things. What's the ideal gas law? PV equals mGT. Yeah. So in 2D, oh, you thought I had it hidden, and no, totally random. So in 2D, we can calculate that the pressure is going to be nKT over A. Okay. So this makes good sense, right? If we increase the thermal energy, we increase the velocity, the average velocity square of the particles, they're going to hit the walls harder. Okay? We increase n, there's more of them hitting the walls. Right? If we decrease the area, they're going to hit the walls more frequently. Cool? So this all makes good qualitative sense on how we expect this to be. Okay. So compare the particles with each other. No, not yet. Okay. So This is ideal gas, which means the particles are non-interacting. So if two particles are on a collision course, they just go through each other. Cool. So again, we're starting with the simplest possible system. Yeah? Okay, so these are all variables that we can control when we set up our system, right? Whatever KT we choose will change what velocities we assign to the particles. We obviously can put in as many as we want. We can define these bounds where the walls are to be whatever we want. Cool? P is something that we would like to measure out of the simulations. And if we can calculate P, then we can try and verify the ideal gas law. Okay? So we need a way of calculating P. What is a nice general definition of pressure? Especially in the context we're talking about. Pardon me? Yeah, it's the force per area. Okay? So really, if we want to find the pressure of the system, what we want to do is calculate the average force on the walls and divide it by the area of the wall. In 2D, this is going to be the force over the perimeter of our system. Okay? And so if we take it to all have the same distance L, this would be over 4L. Cool? Again, that's just a 2D analog reading. Okay, that's great, but now I need a way of calculating the average force. Well, how can I calculate the force? The force comes from a particle coming along with some velocity v. Okay? It's going to hit the wall, and in our simulations, all we're going to do is if a particle is traveling this direction, and we find it on the other side of the wall, we're just going to bounce it backwards. Okay, we're going to take whatever position it had. So let's say we find it here. And so this is some distance here, delta x. We're going to place it at delta x back inside the box and give it a v going this way. Cool? So we're just going to reflect the particles. Yeah? Okay, well, we can calculate the force in this transition. Because the force is the change in momentum over the change in time. Okay? We're doing this discrete, so it's dp over dt. What's momentum equal to? Pardon me? Yeah, mv, that's some velocity, right? So what's our delta p equal to? It's just going to be mv before the collision minus mv after the collision. Okay? But this guy is just negative v before the collision. Right? So, what do we get? We get 2mv before the collision. Okay, and then this is all over the delta t. And the delta t, what's the delta t going to be? In the simulations, what's my delta t? This is a time step. Okay? This momentum is transferred in one time step. Okay? So whatever time step I'm using in the simulations is my delta t. So let's call that be a little delta t here, because we want the little delta, we want it small.
Couldn't that kind of mess up your simulations though? Like if you choose a huge time step, like couldn't you get lower forces on your walls? If you choose a really high time step, wouldn't you inflate that number?
No, it works out.
Okay.
Fewer velocities.
You'd probably be okay.
Right, because they're on both sides. But
Austin, until your particle could actually go from one side of the box to hitting the other wall. Okay. But until then, it doesn't matter.
Yeah. So why doesn't it matter? We increase the time step. What happens?
There's nothing happens between collisions and the wall. So, right. Nothing.
Yeah. Okay. So what happens now is if you have a very small time step, when you calculate the force at each time step, you're going to get a lot of zeros, right? Because no particles are hitting the wall, and every now and then a particle hits the wall, and you get a non-zero result. If you increase the time step, you get those zeros. Now you can have within a single time step, you might have a couple particles. Before you would see those as individual events. Now they would just be flat to one number. But you're obviously going to get the same number. You can add them all.
In fact, if we make the time step too small, we might get rounding error.
We always get around.
Yeah, but if we only have one particle hitting the wall, we're dividing it by at the 20 degree then.
Yeah, for sure. Yeah. Cool. So it doesn't actually depend on the time step. Cool. Because that's really like it's like our sample. Cool. Yeah. Okay, so what do we do then? Well, we calculate exactly that each collision with the wall contributes to m, and its pressure, I don't care if it's a positive or negative velocity, so I can just take the absolute value over delta t. And so this, every collision we have will give us this contribution to the force. We calculate the force at each time step, and then we just add up all the forces at each time step and divide by the total number of strikes. Cool, and that gives us our average. And then all we have to do is normalize that by 4 times L, and we get a pressure. Cool, fair enough. We're all on board. Okay. Okay, so here's a program to do our ideal gas. Again, things start out the same with our headers, our main function here. I'm going to define L to be, the length of the box is going to be 50, with X and Y. Cool. I'm going to have 100 particles in there. And then I'm defining a bunch of arrays statically here. So we haven't seen this yet. This is just how you define an array statically in C. Okay, so what this means is that I can now have a data element here, AX. So if I have 100 particles, I can have AX at 0 is the acceleration in the X direction for particle 0. AX at 1 is the acceleration in the X direction for particle 1. Cool. And then I also have the acceleration in the Y direction, velocity in X and Y, and the position in X and Y. Because of course these are the 3 variables we're primarily interested in when we do simulations. Cool. This is just some syntax. All right.
Is that like a vector? 99999.
Oh, that is just, I'm just putting a relatively large number in there because I know I'm not going to sample more than that. Okay? If you knew you were going to do 100 particles, you would put 100 in there. Okay? But I wanted it so that we could increase this to 1,000 if we wanted to. Okay? This is kind of just an artificial limit. It's bad coding practices. Okay. All right. This VH is, remember, we're going to use the velocity variolet, so we need the velocity at the half step. We don't need to actually store that, but we just need it for every particle, so it can just be a single value. Cool. That's going to change all the time. Then we have our force, our time. Tmax is going to be 1,000. We have typical values here, so often when we do simulations, especially when we're trying to do proof of principle like this, we set everything to 1, because 1 is an awesome number. Okay. We'll keep gravity at 9.8, just to remind us we're on Earth. I'm just going to set pi. I'm going to open a couple files here. One of them is going to be an XYZ file, so that this is where we're going to dump the coordinates to, so that we can view the simulation after it runs. I'm going to have the velocity dumped to 1, and I'm also going to have what I call the observable dumped to another one, which is really just the average force. Cool. So the first step is to initialize the system. So for I less than n, where n is 100, I'm going to go through and assign positions and velocities. My positions are easy because they aren't interacting. I don't have to worry about overlaps. So I just take a random number between 0 and, or actually no, I'm going between negative L over 2 and L over 2. Cool? So that just dumps it somewhere in the box, somewhere on X between negative L over 2 and L over 2. In the Y direction, I'm going to do the exact same thing. Okay, dispersed. Cool? Is everybody cool with that? All right, so here you can see the use of the array here. I is just going to increment from 0 to 9. It's going to give different X and Y position. Cool? Yeah? Any questions? No. Okay, so then I want to do the velocities. But remember, for the velocities, I want this Gaussian distribution. So what I'm doing here is I'm drawing two linear random numbers between 0 and 1, and I'm popping them into the Box-Molar transformation, which is one of the techniques we talked about, so I didn't derive it. Okay? And this will then give me Gaussian random numbers, the appropriate mean and standard deviation. Cool? Okay, so those I can then assign to the X and Y velocities of my particle. Cool, and that's all the initializing I need to do. I need to give every particle a position and every particle a velocity, and then I'm done. Cool? Okay. Then we get into the actual loop where we want to integrate the system. So we want to evolve it in time. So this is the actual simulation. What do I do here? Well, while t is less than t max, what I'm going to do is I have to loop over every particle in the system. And this is just a velocity-Verlet integration algorithm that we talked about last time. So I calculate the half velocity, I calculate my new position, I calculate my acceleration based on the new position. But in an ideal gas, what's the acceleration of every particle? What's the force on every particle? Except when it's at the walls, where we're just going to manually reverse it. 0. Okay, so there's no acceleration. Cool. There's no force in this. Okay, and then I can get my new velocity. Okay, so this is just doing the velocity-Verlet algorithm in X and then in Y. Cool. Now I have to check for violations of the boundary condition. So here, I'm going to have, if the particle is outside the box, I'm just going to reverse its velocity. Okay, that's all I'm going to do. Right, you straight outside the box, just reverse your velocity as if you collided. Okay, the time step is small enough I don't actually have to worry about it so much translating the position. I'm going to catch it like it's soon. Cool. Any questions on this? Okay, and that is it then. So this is very simple molecular dynamics simulation. We don't even have acceleration. And it's going to give us an ideal gas particle. Yeah? All right, let's see if this compiles and runs. Hopefully.
So the velocity-Verlet is like major overkill here, right?
Yes, it is. But we want to keep using it through the rest of the stuff. So we're just going to keep that here. Totally is. Okay, so compiled, and I'll run it. It's already done. And let's go back to the program now. So it's spit out some numbers there. And what I'm doing is that every time I have one of these wall events here, remember those contribute this 2m times the absolute magnitude of the velocity over the time step to the average force. Okay? So whenever I detect one of these collisions with the walls, I'm just going to add that factor to the force. Cool. And then at the very end, all I need to do is take the average force and divide by the total number of frames, which is the number of integrations. And that will give me the average force on the wall at any point. Is that good? Yeah? And of course, the average force on the walls, we can get the pressure out of that by just dividing by 4. And so the numbers spit out at the end are the average number of collisions, which we're not going to use here, and the pressure. So basically, the pressure that and calculated in my simulations is 0.03. Cool. Okay, we'll come back to that in a minute and check if it's right. But first, let's visualize the results. I'm going to open VMD here again. Ideal.
Some funky visualization.
Yep. So let's clean that up a little bit. Okay.
Yours has a really, really tiny velocity.
Yeah, really low.
No, you're probably never gonna, no, yes.
So these were given a velocity at the very start, and then it was just not changed after that. Like whatever they had, just the entire way, which is why that one on the top side is just kind of bouncing up.
That's right. And so you can see in the simulation that we reach.
Yeah.
How's it big enough to plug in?
That's just the loading. That's an artifact of loading.
Oh, okay. Yeah, probably cost.
Cool.
The moment calculation starts.
Yeah. Okay. So this is not very fancy, but this is the basics of molecular dynamics. Okay. Ideal gas. So now let's check the. Yeah. So now if I play it, should. Okay, so let's check the results now. Yeah. So my ideal gas in 2D is NKT over the area. And if I take N equals 100, I set KT to be equal to 1. L is 50, A is L squared. I plug that in, I get 0.040, and the simulation gave me 0.03. Okay, and so you can play with these numbers. You could plot it for different system sizes and plot against velocity, and see that you get a decent agreement with the ideal gas. Okay, of course, I could get better agreement if I ran the simulation for longer. Okay, but it serves enough to demonstrate. Cool. Any questions on this? So again, we're slowly building up to where we want to get. Okay. So what do you think the next thing we want to do in our system is to make things more interesting?
Put gravity in?
Well, yeah, no, that'd be interesting, but we're not going to do that yet.
Interaction.
Yeah, interactions between particles. Okay. If we looked at that, we saw the particles cruising right through each other. Okay. And that is not necessarily so physical. So I got a couple minutes left here. Not a while. Actually, you know what? We'll save it for next time.
Yeah.
Yeah. So, which is tomorrow.
I think like the third.
You